Hello, welcome to College Algebra, section 5.3. We're right in the middle of section 5.2 and 5.3 being kind of the same concept, a little bit more difficult concepts here in 5.3, graphing some rational functions. I wanted to remind you I have a little bit different notes, techniques. I always try to find the vertical asymptotes first by setting the denominator equal to 0, then locating the horizontal asymptotes, which really we should be calling the ending behavior asymptotes because they might be oblique, which means we're going to divide to find the equation of that. To find out the horizontal or the oblique asymptotes, we look at the degree of the numerator. If the numerator is less than the denominator, then we stick Mrs. Y at 0. If the numerator is equal to the denominator, then we look at the coefficients out front and divide A divided by B. And then if the numerator is greater than the denominator, then we divide the entire numerator by the denominator and come up with some kind of an equation for the oblique asymptote. It doesn't always have to be linear. In this section, I'll show you where it's a quadratic oblique asymptote. X-intercepts, we're going to set the numerator equal to 0. There's an exception to that if there's a D shift or a K shift. Vertical shift, then we're going to have to go back to our original definition for x-intercepts and let y be 0. And then to find the y-intercept, we're going to let x be 0. We'll let every x be 0, and we'll find the y-intercept. So here's the book's notes. You can read through those, or you can follow my notes. I've kind of condensed it for you a little bit. This looks a little bit more, to me, it's too much to read. Okay, so I'll show you a couple things. To find, there's my notes over here again, just so you can see what's going on. To find the vertical asymptotes, I set the denominator equal to 0. I would always recommend trying to factor this first to look for any removables. There are none, so it looks like there's two asymptotes, vertical asymptotes at x equals 2 and x equals -2. Next, I'm going to try to find the horizontal asymptotes by looking at the degree of the numerator is a 1. The degree of the denominator is a 2, so since the degree of the numerator is less than the degree of the denominator, that's what this says right here, y equals 0. To find the x-intercepts, I set the numerator equal to 0. So looking up here, when does x minus 1 equal 0? And that's when x equals 1. I'll plot that point. Looks like I'm going to cross the horizontal asymptote, which I can. I call the horizontal asymptote mom. And you can cross mom as long as you have a reason. She's full of love, mercy, tender, and grace. She'll forgive you, but just don't cross dad. That's the x equals. So the y-intercept is found by letting every x be 0, and you can find that by just looking at pretty much the last numbers out there. So it's going to be 1/4 if you let every x be 0. So we found another nice point. You got two wonderful points to be able to connect. We'll connect those points together. For those two dots, I'll keep swooping toward the asymptote. This is a single root, so I'll pass. And then it's a single asymptote. So since it's a single asymptote, I'm going to if this goes to negative infinity, I'll start up in positive infinity, swoop toward the asymptote, no reason to cross mom, and similarly on this side. This does have some pretty nice symmetry, although not all of these functions have symmetry. So we had an x-intercept at 1, 0 and a y-intercept at that 1/4. Here's how the book went ahead and graphed it. I'm not a big fan of plugging in for x and solving for y because I think for this you just kind of want some general x and y intercepts and some swoops, so you don't need to be as accurate as the book is asking you to be. This is talking about if this goes to positive infinity, then it picks up in negative infinity because this is a single asymptote. Later on we're going to look at double asymptotes, and that's where you get the volcano effect or heading in the same direction. So here's the book's answer to the graph. We were pretty close. We never found this point. You don't need to. I know that it just swoops this way, passes through this point, and swoops toward the other asymptote. You don't need to be as specific to find those points. This next example, again, trying to find the vertical asymptote, set the denominator equal to 0, so that's just x equals 0. The y-intercept, looks like the degree of the numerator is greater than the degree of the denominator, so I can divide. Either you can do long division or synthetic division. It's kind of weird to synthetically divide by a 0, but it actually works. If you synthetically divide by a 0, we get, what, the coefficients of 1, 0, -1. Bring down the first term, multiply, and we get y equals x. And that's the equation of the horizontal. Well, it's not even really horizontal. It's oblique because the degree of the numerator was greater than the degree of the denominator, so I just did a quick division. So that says start at 0 and rise 1 and run 1. To find an x-intercept, set the numerator equal to 0. I could have factored this thing, I suppose. It makes it a little bit easier to see. I got an x-intercept at 1, another x-intercept at -1. 1, 0, and -1, 0. And then the y-intercept is let every x be 0. Well, that's not going to work because, well, a couple of reasons. You can't cross dad, so there's never a good time to cross the x-intercept. So I can't put a point on the x-intercept. I would say none over here. There's no x-intercept because you can't divide by 0. Besides, we don't want to cross dad. So I've got two pretty good nice points here. I'll start at this point and swoop toward the asymptote, and start at this point and swoop toward the asymptote. It's a pretty good graph. We'll see again, the book goes through a lot of rigmarole, but they get kind of the same kind of solution here. All right, for this one, we'll find our VA. Oh, this one's really interesting. I have a hint down below, and the hint says that one of the asymptote is linear, but the other asymptote is quadratic, which I don't think I've ever shown you before. So this kind of gets a little bit funny. The vertical asymptote is found by setting the denominator equal to 0, and actually this is a double asymptote. You might want to write x equals 0 twice to remind you that the function's not going to alternate from positive infinity to negative infinity. It's going to either be a volcano going up in both directions, or it might be going down. I don't have enough information. I'll keep working through this problem, but I know that I'm going to go the same direction on both sides of that x equals 0. The horizontal asymptote is the weird one because the degree of the numerator is greater than the degree of the denominator. If I do that synthetic division again by 0, this is, in fact, let's do the long division this time because it's a little bit, I'll have to synthetically divide twice by 0 because it's a double root. So let's just do long division, x to the 4th plus 0x cubed plus blah, blah, blah plus 1. So x squared goes into x to the 4th, x squared times, and then it never goes into any of those, so plus 0. So it's just really y equals x squared, which is funny for asymptote. Over 1 up 1, over 2 up 4. Get a little bit more accurate here. So this purple is my oblique asymptote, which happens to be a quadratic asymptote. I know, that's weird. So let's see, the x-intercept is going to be found by setting this equal to 0, so there's none. No x-intercepts because x to the 4th plus 1 never equals 0. And then the y-intercept, letting every x be, there's none there either. So when there's no x-intercept or y-intercept, there's no point. I would just do a quick let statement, and let's let x equal 1 and see what happens. If we let x equal 1, we get 1 to the 4th plus 1 over 1 squared, so that's just 2. So I'm going to go over 1 up 2. There's a nice point, and then from that point, I'm going to swoop toward the asymptotes. And I can't cross dad, the red one, so this kind of is in here. And believe it or not, this does have symmetry. You can actually test a -1, but there's over here, there's another point over here. If you let x be -1, you'll also get a 2, and that means that there's another piece of the function. Right in here is where that volcano effect is happening, where we talked about before. That's that double root, so that's why it's happening on both ends. So that's why I don't even really need to test this point down here. I knew if this went to positive infinity, this side also goes to positive infinity, so I could have just swooped in here, and I don't want to cross that oblique asymptote. There's no reason to cross. So here's how the author of your textbook solved it. There's a little bit better and zoomed in picture of the graph. For this one, I would go ahead and factor this first, looking for any removable. That would be a whole for the function. So up top, we can factor out a 3x, leaving me with x minus 1. And down bottom, I think factors of 12 that differ by 1 are 4 and 3. Signs are different. The larger term is positive. And it doesn't look like anything cancels. So I'm going to say the vertical asymptote comes from the denominator. X equals -4 and x equals 3. So I'll graph -4 and 3. The HA, since the degree of the numerator is equal to the degree of the denominator, I look at the coefficients out front, A over B. And this type, it's going to be y equals, well, it's a 3. 3 over 1. So that's y equals 3. Horizontal. The x-intercept would be let the numerator equal to 0. So this would cause as 3x to equal 0 when x is 0. So 0, 0 is an x-intercept, and this is my other x-intercept when I set that equal to 0. So I have two x-intercepts. And by the way, if 0, 0 is an x-intercept, guess what? The y-intercept is also 0, 0, because I've already defined it. So I've got two choices here. Either the function is going to swoop over or it's going to swoop under. And just by the look of things, without actually plugging in for x and solving for y, my guess is it would swoop over because I probably don't want to cross mom if I don't have to. So I'm going to guess that it's swooping away from mom because I don't have a reason to cross mom. If this goes to negative infinity and these are single asymptotes, they're going to alternate. So this is going to start in positive infinity, swoop down. And actually, that was a good guess because if I would have turned this graph around and graphed it this way, which would have been weird, then if this went to positive infinity, this would have picked up in negative infinity and I would have created another root right here. And I know that there is no root here at this flower, so I can't do all of this happy face, smiley face stuff, so I'm going to back out of all that. And so I'm fairly convinced that this is the way that the graph, without even graphing a point, I know this is what it's doing. If this goes to negative infinity, it picks up in positive infinity, and there's another piece of the function over here. So swoop, swoop, swoop with a couple points. So here's how the author is graphing it. Again, don't worry, it doesn't have real good symmetry here, but we don't need real symmetry. And they plugged in some, I do not expect you to find these points, especially without a calculator. Who's going to plug? Don't even plug in a -5. Your graph might look like this, but that's fine. I'm not looking for accuracy, I'm just looking for understanding. So if you were to look closely at these functions, they might be doing some really weird things in here. This is just showing you that there's not symmetry here. And this is actually saying that over here, this swoop isn't as normal as you think. It actually kind of does a swoop with a little dip in it, but I don't want you to have to worry about all that. We're not going to use our calculators to find the minimum and do all that stuff. You'll just graph a nice little swoop like we did. Don't get too detailed. So all I want is for you to factor these things and give me your best. Well, let's see. Are there factors of 2 and 2 that add up to 5? How about 4 and 1? So the outer terms are 4 and 1. That adds up to 5. Signs are going to be alike. They're both negative. So here is an example where I actually can cancel something. Now this is called a removable, which causes a hole in the function. And so I'm really going to be looking at graphing just the 2x minus 1 over x plus 2. So this is the function that I'm going to look at when I start trying to determine my vertical asymptote. I'm not going to say both of those because I removed this. That's not an asymptote, that's actually a hole. So the only asymptote I have is x equals -2. Good thing I factored first to see if I could simplify. I would hope that you do the same thing. The horizontal asymptote, the degree of the numerator is a 1, the degree of the denominator is a 1, so I'm going to do my coefficients, a over b. And in this case, I think I'm going to end up with a y equals 2, because it's 2 divided by 1. The x-intercepts, I'm setting the numerator equal to 0, so this equals 0 at 1/2. So I'll put a point here at 1/2, 0. And then the y-intercept, letting every x be 0. I'm just looking at this last thing, -1/2. Looks like a good y-intercept. So I've got pretty good 2 dots here. I'm going to connect those 2 dots, keep swooping toward the asymptotes, and keep swooping toward the asymptote. But I got to go back and remember I have a hole here, and I have a hole at 2 comma something. And to find the something, I'm just going to evaluate this function f at x. I'm going to evaluate at f at 2 because this is my y value, f at 2. So to find f at 2, it's 2 times 2, which is 4 minus 1, which is 3, and then 2 plus 2, which is 4. So my hole, it'd be nice for you to record this on the day of the test, 2 comma 3/4. I'll see if that matches my function. I'm going to go back and grab my eraser and actually go over 2 and up to, boom, right there is a nice little hole. So over 2, up 3/4. And that matches pretty good with my function, over 2, up 3/4. You can see there's actually a removable there, not an asymptote like I originally thought at x equals 2. So I get rid of this vertical, I get rid of that vertical line and just replace that vertical line with a hole in the function. That's called a removable. So again, here's how the author works that out, and he's explaining how this swoops, but there's his hole right here. So if you graph this on a calculator, that hole actually won't appear. But if you hit trace to enter, you won't get a 3/4. You'll just get a y value of nothing because it's undefined. You can't let x be 2. in the original function because that will cause you to divide by 0, so it's actually an undefined value. But if you wanted to find where the hole is at, you could plug it into the simplified version. I love these types of questions because this is going to go backwards. They're asking you to come up with the equation after I give you a graph. So we've been giving you equations and asking you a graph. Now I'm going to say, hey, come up with a graph. So remember, the numerator finds the x-intercepts. Or if we set the numerator equal to 0, you get x-intercepts. So the x-intercepts look like a -2 and a 5. So I know that I'm going to have an x plus 2, because when I set that equal to 0, I get the -2. And then to have a, if the root is 5, the factor is x minus the root, because I always set the factor equal to 0 to find the root. However, you need to remember from our discussions earlier that a double root bounces. So since this is bouncing, I'm going to square this guy to denote that, hey, I'm bouncing off. I'm not passing through. Like this one's passing through, so that's just to the first, and I won't put a 1 over there. But I can envision that there's a 1 there. Now, the denominator comes from these asymptotes. And it looks like I have an asymptote at 2 and -5. So I just have to say x minus 2 and x plus 5. Remember, whenever you see parentheses, change the sign. So that x plus 5 actually gives you the asymptote of x equals -5. Now, something's wrong here because I can see from my graph that I actually have a volcano effect happening here. So it looks like on the left side it's going to -infinity, on the right side it's going to -infinity. So it looks like this is not a single asymptote where it's alternating. One side goes to positive and the other side goes to negative. That's a single. If it goes the same direction, it kind of forms this volcano down here. It's an inverted volcano. Then I need to square this asymptote. So it's really a double root x minus 2 quantity squared. And that's what causes this function to head off into the negative direction on both sides of that vertical asymptote. So now let's look at the degree of the numerator. The degree of the numerator is actually x cubed if you multiply all this together. The degree of the denominator is also x cubed if you multiply that together. But I can see that the horizontal asymptote is not at 1, it's at y equals 2. So I would place, you can put an 8/4 here, but that's kind of, anything that reduces to a 2 would work for me. I would just stick a 2 out front. So your final equation would look something like this, with a 2 out front, because the horizontal asymptote, the degree of the numerator, so it's a 2x cubed over it, just x cubed. If you think about it, if you multiply this out, this is 2x cubed plus other stuff over just an x cubed plus other stuff, and you can see that the horizontal asymptote now is y equals 2. The degree of the numerator is equal to the degree of the denominator, so you do that a over b business. So I really like the concepts here because it talks about the double asymptotes going on, and you can write equations from the given expressions. Here's a word problem which I'm going to omit because you have to use your calculator, and for the next section we're not using our calculators. So I have a couple other examples. Again, you might think to quit watching the video now, but each example is a little bit different than the next example. So as soon as you think that you kind of understand these, then something new or interesting happens. So I'm going to keep working. Hopefully you'll keep watching. I've already gone 18 minutes, so I'll try to buzz through a couple more of these. I'll post this worksheet online on Blackboard, and I would encourage you to go to Blackboard and try to work the worksheets. You'll be surprised. Watching me do it seems really easy, but when you try it yourself, you're going to struggle trying to figure out where to graph these. All students do. Students have a hard time with this section. So my suggestion would be go to Blackboard, download this worksheet, try to graph a couple of these things. Most students will get the VA correct by setting the denominator equal to 0. Most students will get the HA perfect. Not a problem. They look at the degree of the numerator, the degree of the denominator, decide, oh, that's y equals 2. So students don't have a problem with graphing x equals -1 or y equals 2. Students don't even have a problem with the x-intercept. And the x-intercept is found by setting the numerator equal to 0. So students will have the correct answer over here of -1/2, 0. And they'll even put a point there that everything's good so far. They'll have the correct y-intercept. So students usually do a really good job at filling in information over here. And this is why I ask them to do this on their test, because at least they can get partial credit if they can tell me that the y-intercept is +1. That's the easy part. For some reason, students have a really hard time just graphing these things. So please take the time to try this on your own, because just sitting here watching me work this, for some reason, just too difficult. So this one looks pretty straightforward. Just swoops, and it's going to alternate. Just going to swoop. For this next example, I don't even think this first example was on your worksheet. So it says go to the next slide, because your worksheet is going to start with example number 2. So apologize for that. So let's see. This time in the vertical asymptote, there is none, because you can't set that equal to 0, so there's no dad in the house. The horizontal asymptote, since the degree of the numerator is a 0 and the degree of the denominator is a 2, it's y equals 0, because the degree of the numerator is less than the degree of the denominator, then y is at 0. The x-intercept is found by setting the numerator equal to 0. Well, 4 never equals 0, so I'm going to say none. Undefined. And then the y-intercept is by letting every x be 0, it looks like it'd be 4 over 1. So at least I've got one good point, 4, 0. The mistake here that students will make is they'll draw something kind of blocky here, or they'll come down and give a nice sharp edge here, and I don't want any of that. Remember, these are polynomials, nice, smooth, rounded edges, so make sure you swoop in the correct direction. Call this the hump function. Kind of looks like a mound. All right, this one we got a double asymptote. Sometimes to remind me that I have a double vertical asymptote, I'll even write it twice, x equals 1, x equals 1. What does a double vertical asymptote mean? And I'm going to have that volcano effect. Either it's swooping, again, positively on both sides, or it's going to swoop negatively. I don't have enough information yet, so I'm going to continue finding some points and some other things before I make that determination. But sometimes it's helpful to write it twice, because by the time I get done to graphing it, sometimes I forget. So the horizontal asymptote, the degree of the numerator is x to the 0, the degree of the denominator is a 2, so again, y equals 0. The x-intercept is found by setting the numerator equal to 0. Again, 2 never equals 0, so I'm going to say none again. And hopefully I've got a y-intercept. If I don't, I'll just do a let statement. Well, looks like I do have a y-intercept. So if you let x be 0, it's 2 over negative 1 squared, which is a 2. So this one looks like I've got a point. I'm going to start at the point, swoop toward the asymptote. No reason to cross mom down here, so just keep heading off. And since it's a volcano, because I remembered I had 2 of them, then it's heading in the same direction. So just give me a swoop over here. If you want to be really accurate and find nice point values over there, you can let x be 2 or let x be 3 to verify that it's over there, but that's a waste of time as far as I'm concerned. Any kind of swoop over there will do for me. All right, so here, vertical asymptote, it looks like there's going to be none, because when you set 3x squared plus 1 equal to 0, you can't take the square root of a negative, so I'll say none. Okay, no vertical asymptote. So similar to the last problem. The horizontal asymptote, the degree of the numerator is 2, so how about 3 over 3, which is y equals 1. So a nice horizontal asymptote at y equals 1. The x-intercept, set the numerator equal to 0, and I think that's going to be 0, 0. And by the way, if the x-intercept is 0, 0, the y-intercept is always 0, 0. You can let every x be 0 if you want, but I know it's going to be 0, 0. So again, kind of tricky. You should try to graph this yourself, because I know students do really strange stuff, like they'll cross the asymptote, and I don't know what you guys do. Sometimes you cross it like this, and I don't know why. There's no reason to cross. Oh, I have some people do sharp edges like this. Again, these are polynomials. These would be smooth edges. I'll have some people come down and create another x-intercept where there are no x-intercepts other than at 0, 0. So you need to come down, touch. Since it's a double root, you're just barely bouncing right there. And how do I know it's a double root? Because it's 3x minus 0 quantity squared. And that's telling me to bounce right at that 0, 0. This one also has a double vertical asymptote. It looks like it's at x equals 2, but I'm going to write it twice to remind me that it's another volcano effect happening at 2. The horizontal asymptote, since the degree of the numerator is less than the degree of the denominator, because the denominator is a 2 and the degree of the numerator is a 1, it's at y equals 0. To find the x-intercept, I'll set the numerator equal to 0, and I'll get 0, 0 for the x-intercept, which forces the y-intercept also to be. Now this is interesting, because I don't really know if the function does this through the blue and comes back, or if it does purple. Wait a minute. Let's see. Yeah, that's a single, so it's going to pass through that root, but it might start at negative infinity, but it might start in positive infinity, and I don't really know if I should graph blue or purple. So since I don't have any points except for the 1, 0, 0, I would just do a quick tester point. And it looks like I kind of want to know what's happening over here. So I'll test a -2. And all I really need to know is the y value positive or negative? Because if it's positive, then I'll choose blue. If it's negative, I'll choose purple. So let's just plug in a -2 and just tell me if it's positive or negative up here. Well, the opposite of a negative is positive, and anything squared is positive, so now I know it's the blue function. So if I'm going to graph the blue, I'll follow the stars. If this goes to negative infinity, I got to remember it's a double asymptote. So that means it starts in negative infinity down here as well and swoops toward the asymptote. If it wouldn't have been a double asymptote, then I would have been up here. So I'll go back and erase the purple so that nobody gets confused about what this final graph looks like. But you should run your test point. For this one, I'm going to look for if there's any holes, because I might think that the asymptote, there's 2 vertical asymptotes, but after I factor the numerator, something might cancel and that might create a hole here. So factors of 4 that add up to 5 are 4 and 1. Signs are alike. They're both negative. And in fact, let's see, this is going to be a 2x and x. Got to be 1 and 1. And there it is. 2x and x adds up to 3. So plus 1, and oh, nothing cancels. So my VA comes from the denominator. X equals 4 and x equals, these are single. I've got 2, but they are single, so they're going to alternate. So I got 2 vertical asymptotes that are going to alternate from positive negative to negative positive. So the HA, the horizontal asymptote, since the degree of the numerator is equal to the degree of the denominator, I'm just going to do this A over B. In this case, y equals 2. The x-intercept is found by setting the numerator equal to 0, so it looks like I have 2. -1/2 and a -1 for my x-intercept. So -1/2 and a, oh, wow. These are 2 points really close to each other. Barely get them on my graph. Is that right? Yeah, negative, yep. Y-intercept is found by letting every x be 0. It's these numbers right here. If you let every x be 0, you're just left with 1/4. So 0, 1/4. And that's right here. So this is too small to see what's going on, but since these are single roots, I'm going to pass through both of those. It's hard for me to draw this in because it's so tight. Wow, this is a great problem. So the question is, what do I do from here? Should I try to go to the right? No, I can't cross dad. Should I try to come back down? No, I cannot create another x-intercept. Can't go right, I can't go down. I can't come back left because then it doesn't pass the vertical line test. This has to be a function. So the only way that I can go is up. And Mom will forgive me because she's full of love, mercy, tender grace, because I can't go down, I can't go right, I can't go left, I can't go anywhere else besides going up. So this goes to positive infinity, so I know it alternates to negative infinity. I can't cross, so it doesn't come up that high, so it must just stay down here somewhere. And if this goes to negative infinity on the right, it picks up in positive infinity. And that kind of makes sense, because if I would have done anything else, then I would have had a function down here, but that would have created another x-intercept. So I can't draw anything down there because it wouldn't pass the vertical line test, and I don't want to because I don't have any other x-intercepts. So actually, this is a non-symmetrical graph, but that's a great problem. I can work that in class tomorrow. Nice. So number 7, let's factor this thing. Factors of 2 that differ by 1 are 2 and 1. Signs are different. The larger is negative. So I got 2 vertical asymptotes. X equals 2 and x equals -1. Kind of missed my -1. I'll be a little bit more accurate. All right. So the horizontal asymptote is found, the degree of the numerator is less than the degree of the denominator, so it's y equals 0. The x-intercept is setting the numerator equal to 0, so 0, 0, and if the x-intercept is 0, 0, the y-intercept is always 0, 0. So again, I'm going to have to do a tester because I don't know if this function does this in blue or it might do this in purple. I'm checking to see, yep, that's a single root. So I know it's passing that point. So it's this function definitely will not come down and bounce. There's no u in here. There's got to be an s because this is to the first power. But I don't know if it's a blue or a purple. So again, I would do a quick tester point, and it looks like I'm interested in letting x equal 1. So let's let x be 1, and again, all I need to know is if it's going to be positive or negative. So this is going to be positive 1 over, see, 1 minus 1, oh, that's a negative number here. So I know the y, if I let x be 1, I'm a negative number, and negative means purple. So I'm going to draw in the purple. If this goes to positive infinity on this side, it'll pick up in negative infinity. I never drew in my horizontal asymptote. And if this goes to negative infinity, it picks up in positive infinity. Let's get in that horizontal asymptote at y equals 0. I never drew that in. That's what the function is approaching. So there's a couple other problems. These are amazing, 9 and 10, but I'm going a little bit long on the worksheets, or on the videos. 30 minutes is plenty. So thank you for staying with me as long as you did. If you have questions, email me.